Hello friends, I am Snehal and I am teaching you physics. Today we'll see some problems on electrostatics. So let us start. So this is our first problem. Two charges Q1 equals to minus 4 Coulomb and Q2 equals to 16 microcoulomb, it's microcoulomb, are kept at distance 9 meter away from each other. So there are two charges kept at some distance away from each other. Find the point where charge of 5 microcoulomb should be kept on the line joining two charges so that it experiences no force. Okay, so this is the statement of the problem. So it says we have two charges. So suppose this is Q1 equals to minus 4 microcoulomb and this is Q2 equals to 16 microcoulombs, and this is R equals to 9 meters. Now we have to keep this third charge Q3 somewhere on this line so that it experiences no force. Okay, now let's imagine what will happen if we keep that charge somewhere in between Q1 and Q2. So let's put it somewhere. So this is Q and it is positive Q3. Now there will be some force exerted by this Q1 on Q3 and there will be also some force due to Q2. So force due to Q1 will be like this, will be directed along this line. Q1 will attract Q3. So this is F31, force on 3 due to 1. And Q2 will repel Q3. So there will be force due to Q2 also. So this is F32, force on 3 due to 2. So force due to Q1 and force due to Q2, they are both in the same direction. That's why no matter where we keep this charge Q3 on this line, the net force on it cannot be equal to 0 if we keep Q3 in between Q1 and Q2. So either we have to keep Q3 on this side or we have to keep Q3 on this side. Now where to keep it? So this charge Q2 is greater than Q1, so we'll have to keep Q3 closer to Q1 so that it compensates the magnitude of this force. Because closer we keep the charge, more will be the force on that charge. So let's put it here on this side and suppose this distance is x. Okay, so we keep Q3 at point P at distance x away from Q1. Now since total force on Q3 is equal to 0, so force due to Q1 and force due to Q2 should be equal. So I can write F31 should be equal to F32 and this is the magnitude of the force. Directions are opposite. This charge will pull it, it will attract it, and that one will repel it. So two forces get cancelled out. Okay, now let's just substitute the formula here. So it is K into Q1 times Q3 divided by the distance between them is x squared, and it is equal to K multiplied by, now it is Q3 times Q2 and distance now is this r plus x. So it is r plus x squared. Now let us do these cancellations. K and k gets cancelled out. Q3 and Q3 gets cancelled out. So it does not matter what is the magnitude of that third charge. So we have Q1 over x squared equals to Q2 divided by r plus x squared. And notice that Q2 is 4 times magnitude of Q2 is 4 times the magnitude of Q1. So I can write here it is 4 times Q1 divided by r plus x squared, and on this side we have Q1 divided by x squared. So Q1 and Q1 gets cancelled. So now let's do this cross multiplication. So we have 4x squared is equal to r plus x squared, and now let's take square root on both sides. So we have 2x equals to r plus x. Okay, now let's take this x on this side. So we have x equals to r because it is 2x minus x, so we are left with this x. So it is equal to r was 9 meters, so x is also equal to 9 meters. Now let's see problem number 2, and problem number 2 is two charges Q1 equals to 10 microcoulombs and Q2 equals to 10 microcoulombs are kept at distance 9 meters away from each other, just like the previous problem. Find the magnitude of third charge, which should be kept at midpoint of the line joining two charges so that the system remains in equilibrium. Okay, so we have again two charges Q1 and Q2. So both of them are 10 microcoulomb and 10 microcoulombs each, and we have to keep some charge here at the midpoint. So this distance is r equals to 9 meters, and we have to find the magnitude and also sign of this charge, which should be kept here so that this system remains in equilibrium. Now notice that whatever charge we keep here, whether it's positive or it's negative, the force due to these two charges on this charge will be equal because this is the midpoint. So this distance and this distance is same, which is r by 2, and whatever charge we keep here, if it's negative, this charge and that charge will pull it with same magnitude, so net force will be 0. If it's positive, the repulsive force due to these two charges will also be in opposite direction, so that the net force on the charge is 0. Okay, so this charge will always be in equilibrium. So we cannot find out the magnitude or sign of the charge by finding the force on this charge. So we will have to find the force on Q1 or Q2. So let's find the total force on Q1. So we know that for equilibrium the net force should be 0. For equilibrium of a charge, net force acting on it should be equal to 0. So let's take this Q1, let's consider its equilibrium. So I can say net force on Q1 is 0 and it is force due to Q3 plus force due to Q2 equals to 0, and obviously it is force on Q1. So force due to Q3 will be equal to, let's call this distance x. So it is k times Q1 Q3 divided by x squared plus force due to Q2 will be equal to k times, we are finding force on Q1, so we should have Q1 and due to Q2, so we have Q2 also, divided by r squared is equal to 0. Now let's take k and that Q1 common, and let's divide this equation by k times Q1, so we get rid of this thing. So we have Q3 over x squared plus Q2 over r squared equals to 0. So we can take this on other side. Before that, r equals to 2 times of this x. So I can write Q3 over x squared equals to minus of Q2 divided by r squared, which is 2 times of x and square of that. So we have Q3 over x squared equals to minus Q2 divided by 4x squared. So x squared and x squared gets cancelled, and we are left with Q3 is equal to minus of Q2 divided by 4. And we have value of Q2, so it is 10 microcoulombs. So Q3 should be equal to minus 10 microcoulomb. So we are substituting value of Q2 here divided by 4. So Q3 should be equal to minus 2.5 microcoulombs. Okay, so it was a simple problem. Let's move on to next problem. Okay, now let's see problem number 3, and it says a ball of mass 1 kg is suspended using a weightless thread as shown in the figure. So we have this ball of mass 1 kg and this is the weightless thread used to suspend it from this rigid support. Then there is uniform electric field of magnitude 1000 newtons per coulomb in the region. So as you can see, we have this uniform electric field and it has magnitude of 1000 newtons per coulomb, and it is in this horizontal direction. Find the magnitude and sign of the charge on ball if it remains suspended. Okay, so ball remains suspended, it remains in equilibrium, and we have to find the charge on the ball, magnitude as well as sign of the charge. Now let's try to solve this. So let us draw all the forces acting on the ball. So we have one force due to gravity. So this is F due to gravity equals to mg, and we have one force due to tension in the string which acts towards the rigid support. So this is tension in the string T, and there will be some force due to the electric field also. If charge is positive, the force will be in this direction, and if charge is negative, then force will be in this direction. It will be opposite to the direction of field. So to find out direction of force due to electric field, let us resolve this T in two components. So there will be this horizontal and vertical component of P. So this is theta equals to 45 degrees. So this angle will be theta. Or because it's 45 degree, this is also theta. So let me call this one theta. So this component is through the angle. So T cosine theta. And we have this another component, T sine theta. Now if this ball remains in equilibrium, then there should be equilibrium in vertical as well as horizontal directions. So for equilibrium in vertical direction, we should have this T sine theta and force due to gravity. They should cancel each other. And also for equilibrium in horizontal direction, we should have a T cos theta and force due to electric field in opposite direction, so that they will also cancel out each other. So force due to electric field will be in this direction, opposite to T cos theta. This is force due to electric field, so I will put suffix E, and it is equal to, we know, Q times E. Now because the force due to electric field, okay, let me put suffix capital E here. So because the force due to electric field and the electric field, they are in opposite direction, this charge must be negative. So charge on ball, which is Q, it is negative. Okay. If charge were positive, the force could have been in direction of electric field. So by resolution, we get to know that force due to electric field on ball is in opposite direction to electric field. Therefore, charge on ball must be negative. Then let's find magnitude of the charge. So for that, we have, for equilibrium, the magnitude of this force T sine theta should be equal to magnitude of gravitational force. So we have T sine theta equals to mg, and the magnitude of T cos theta, or T cos theta, should be equal to Fe. And we have T cos theta equals to force due to electric field, which is Q times E. So now this is equation 1. Equation number 2. Let us divide equation number 1 by equation number 2, so that this T will get cancelled out. So T and T gets cancelled out. So on left hand side, we are left with sine theta or cosine theta, so which is tan of theta, equals to mg divided by Q times E. So tan of theta, and theta is 45 degrees, so we have tan of theta equals to 1 is mg divided by Q times E. Now we wanted to find out magnitude of Q, so let's take Q on this side. So we have Q equals to mg divided by E, and let's put the values. So m equals to 1 kg, g for simplicity, let's take g equals to 10. So 1 multiplied by 10 divided by, this is 1000. So let's take this in numerator. So in denominator we have 10 raised to 3. In numerator it will become 10 raised to minus 3. So we have 10 multiplied by 10 raised to minus 3 coulombs. This must be charge on ball. And we can write this as millicoulomb. So Q equals to 10 millicoulombs. Okay. So this was problem number 3. So now we have solved few problems on equilibrium under the electrostatic force. Next time we'll see the electric field due to the continuous charge distribution. Till then, you can also solve some problems. Thanks for watching the lecture.